Modeling complexity. We don't want models that are as complicated as the original. What we really want are models that are limited to what we need from the original to answer a question. We'll begin intuitively, both for your understanding and your need later to explain to others. So a model of a process is related to samples of data by data is model plus correction. A model is something a human can understand, or otherwise why bother? Some correction is required in order to get back to the original data. The complexity of a model is the degree to which the model can explain the topology of the data. So here's some data. Here is a low complexity model, the straight line, and here's a model with higher complexity. So a model is a representation of a data set combined with an algorithm for making predictions. So we have some kind of a representation, and then we can make predictions. So the red here is the predictions of the green. The more complex the representation, the more it captures both the signal and the noise in the data. A model is intentionally simpler than reality. That's why we study them. Now notice that gives us the following paradigm. Signal plus noise, which is data, is model plus correction. The correction here is a theoretical concept. Our goal is to use a model to study a signal. The bias in a model is the degree to which it can represent a signal without any theoretical correction. Low bias means little correction. High bias, lots of correction. Variance is the degree to which a model can predict a signal independent of noise. Let's look at a two-dimensional illustration, data in the XY plane. We split it into a training set and a test set. Now, ordinarily, we would hope to be given two different sets. So this is equivalent to that process. We build the model using the training set. We test the model using the testing set. The difference between predictions and actual gives us some sense of the variance. Linear models are high bias models. They would have to be theoretically corrected in order to obtain a real-world signal, a large correction. But we predict the testing data independent of noise in the training points because we're using a line of best fit. In contrast, let's build a model that is not linear. Test it using the training set. We're going to get a lot higher variance in this case. This is a low bias model. It needs little correction if we had only a little bit of noise. But even modest amounts of noise cause overfitting, creating huge variances. So you see, a model that's too complex and has high variance is unmanageable and could be as difficult as the true model. Nearest neighbors, for instance, can model a topology, but are highly sensitive to noise. Overly simple models, those with high bias, may completely ignore important information in the data. We're going to have to get to where we have a trade-off. This is called the bias-variance trade-off. We'll derive this rigorously later, but the mean squared error is the bias squared plus the variance plus the irreducible error. Now, typically we abbreviate mean squared error as MSE, but I'm just going to call it total error. So the bias decreases with model complexity, the bias squared. The variance increases with model complexity. The minimum of the total error is somewhere between the high and the low complexity. The first case we have is called underfitting. The model is not complex enough. And the other is overfitting. The model is too complex. So there is a bias variance trade-off that guides how we select and modify models. Unfortunately, we will never know the bias. It's a completely theoretical concept because bias is with respect to the original process. But the concept of bias is very useful. For example, let's look at suppressing noise in a time series. So here we have our x coordinate. It's got a little bit of noise. Averages suppress noise, and moving averages suppress noises in time series. So let's do a moving average representation. So as we move across the signal on the top, we'll take averages and use those to give us values on the bottom. So there's our moving average representation of the data. And we get a nice topologically equivalent structure to the Lorenz attractor. But what if we use a window that's too large? We're going to suppress more noise, but we're going to have a lower complexity model. It's going to have higher bias. So what happens with our moving average representation now? You can see it's a bigger window, and we've really changed the topology, the shape of our original data. And topologically, we get something that's not the same. So how do we use bias-variance tradeoff to select window size if the bias is unknowable? So we've reached the limit of intuition. It's great, but we can't do anything solid or useful with it. So we're going to have to look at this whole issue again, this time more mathematically. So to begin with, signal plus noise equals model plus correction. So we sample variables x1 to xn to produce data of size m. A model of the process is a function of the x1 to xn. And it tends to have parameters, or we may say these are weights. There are infinitely many such parameterized models possible, where a model is a representation of the processor system, and it requires correction to reproduce a signal. Models with small corrections can generate good signals. And of course, the ideal is small amounts of noise and little correction needed. This, however, is an ideal goal, and it rarely occurs. The true model is a function of x1 to xn. It's the process itself. A true model has no parameters and needs no correction. It is the true model. It tends to model a high-dimensional, complex topology. That is, F-true is in general unknowable and inaccessible. So how do we model the true model? Well, a mathematical model tends to be of the form, the actual y's is a model in the variables x1 to xn with parameters plus some error. An equation model is a function defined using equations. An algorithm model, a function defined via an algorithm. And then model complexity is the degree to which a model F can become, quote, arbitrarily close to F true. If F true is analytic, equal to a power series on an open set, then the model complexity of a polynomial F is its degree. So model complexity is conceptual, not computable. We can often say which of two models is most complex, but in general we rely on a working assumption. Model complexity equals the number of parameters. Algorithms can have high model complexity. Nearest neighbor methods, for example. If you have labeled data of size m, we can predict the response or label of an unknown data point. And we can do that with k neighbors of this unknown point. Now, if we simply use one neighbor, then we can make a prediction just from this one neighbor. But we could also use all the neighbors. But in that case, we just get an average of all the labels. Here we have the same number of positives and negatives. So this is just statistics. You're estimating an unknown value as an average value over the entire data set. So predictions are regular variables. We often use lowercase. So we'll often write lowercase y1 to yr for a prediction. A hat means after the parameters have been estimated from the data. So after we've estimated the parameters, they have values. And then when we make predictions, they have hats because the parameters had values when we made the predictions. Our goal is, of course, to estimate the true model. And we tend to write f hat as the function f, given that the parameters have been estimated from the data. And these parameters are estimated, of course, from the training data. Accuracy is measured via expected value of a function over all possible data sets. Remember, we have a process that we're interested in. We can sample as many data sets from that process as we want. So we're thinking here as data, almost the data set itself is a random variable and taking expected values with respect to data sets. So the variance is just the variance in predictions due to use of different sets of training data. The bias is the true model minus the expected value from all possible data sets of the prediction, the model. Bias measures how much predictions differ from true labels. And here, of course, again, data means across all possible training data. And notice here that bias, therefore, is based on the choice of F, the choice of the model. The definition also implies that if you have a less biased model, the more sensitive it is to the topology or underlying structure of the data. So let's look at bias, variance, and complexity with our nearest neighbors concept. Given unlabeled data of size m, about the same number of positives and negatives, remember here, m tends to be very, very large. We could predict responses using one nearest neighbor, which is approximately m parameters. Or we could just simply say predict the response using all the neighbors, which means there pretty much are no parameters. So bias is insensitivity to topology of the data. And we see at low complexity, we have high bias because essentially it's just a statistical average. Variance is sensitivity to noise. So using all the neighbors is high bias and low variance. Using only one neighbor is low bias. We could conceivably recover the topology, but even the tiniest amount of noise is going to cause massive overfitting. So here is a sketch of the bias-variance trade-off. The mean squared error is the expected value. I'm not going to write the variables. And then you can see what the main step in the proof is. We add and subtract the expected value over the data of f hat. Now we do some independent noise and standard variance arguments. This is all standard calculation. And we end up with this expression for the mean squared error. And we can rewrite that in three terms: the bias squared plus the variance of the noise. So the result is what we saw earlier. The total error is the bias squared plus the variance plus the irreducible error. It would be very useful for model selection, except we do not know the true model. we should think of it as being something that's perhaps unknowable, and the bias is defined in terms of the true model. Regardless, the bias-variance trade-off is still very useful. If the data has very small amounts of noise, then our bias-variance trade-off looks like this, and we can justify using a higher complexity model. If the topology is not too complex, the model has a small squared bias, then that justifies using a lower complexity model, although this is rare in data science applications. So in summary, the bias-variance trade-off, total error is the squared bias plus the variance plus the irreducible error. Variance is a measure of sensitivity to any noise in the data, the usual concept of variance in statistics. Complexity is a measure of how free the model is in fitting the data. And bias is a measure of insensitivity to the topology, the underlying structure of the data. And the bias-variance trade-off tells us our goal is a balance.